Hi guys, in today's lecture we are going to see about sensors. Okay, so to understand sensors, first we should know how does a robot work. So let me take one simple serial robot. So this is link 1 and then link 2. Then here we have a gripper or end effector. Okay, so this is end effector. In this I have a gripper. Okay, so now it is in this position. Okay, so now I have to make a robot. Here I have kept some box. So this robot has to pick the box and the robot has to keep it in this position. So this is my target. This is my start point. This is my goal point. So robot has to pick the box and keep it here. Okay, so for that, first it has to measure the angle. What is the angle right now? So this is theta 1 and then this is theta 2. Okay, but to reach this, so the robot has to take this portion, this. Okay, so this angle is theta 1 dash and then this angle is theta 2 dash. So the robot right now, the initially it is in theta 1 and theta 2, so which is first position. If it has to move to the second position, it has to take this much angle, theta 1 and theta 2 dash. Okay, so how the robot knows that the robot has to move from theta 1 to theta 1 dash, theta 2 to theta 2 dash. Okay, for that, first we have to sense the current position. So each and every joint has this linkage, sensor, motor, and the gear. Sensor, motor, and gear. So we have studied already gear arrangement, motor in the previous sessions. So now it is sensor. Okay, the sensor will say that the current angle is theta 1. The sensor will say that the current angle is theta 1, and then this sensor will say that the current angle is theta 2. So this informations are given to a controller. So this is theta 2 is given to a controller, and then theta 1 is given to a controller. Already we have joint 1 control system, joint 2 control system. So this theta 2 information will be passed to joint 2 control system. This information will be passed to joint 1 control system. So already this joint 1 is provided with theta 1 dash. Then this joint 2 control system is provided with theta 2 dash. So the joint 1 control system, it compares theta 1 and theta 1. This is my requirement. So it compares theta 1 and theta 1 dash, and then some error is generated. That error is given to a controller. Then this controller will give the actuation, let's say actuation 1. The same thing, the joint 2 control system compares this theta 2 dash with the current value theta 2, and then it generates some error. That error is given to a controller. As a result, this controller will generate the actuation 2. So now this actuation 1 is given to this motor as armature voltage. Then this actuation 2 is given to a motor as armature voltage 1 and armature voltage 2. So now when this voltage is given to this and you have a proper gear system, automatically this link will be moved to theta 2 dash and this link is moved to this one. Okay, so this is how a robot works. So for that, sensor plays an important role which says what is the current position. So we are going to see sensor in this. The same thing is explained in open loop and closed loop. So this we have already discussed in the second unit when we learnt motor. Okay, so here this is an open loop, so there is no feedback. So already the voltage is predetermined. That voltage is given to a DC amplifier. Then it's a single condition. Then this voltage is given to the motor. So as a result, the motor will rotate. Then the shaft also rotates. Sorry, the motor will not rotate. The motor will be energized, and the shaft which is attached to the motor will rotate. As a result, turntable will also rotate. So likewise, you can use this concept to turn. Okay, and we can measure the speed also. But yeah, this is in a schematic representation. So this is the process. Okay, then here's the actuator. Then this is the one. So this is an open loop. Whereas in closed loop, we have to keep one sensors. Okay, that sensor is, so your tachometer is velocity sensor. Okay, velocity sensor, it senses the voltage, then it will compare that. So like for example, we have said that this is theta 1, then this requirement is theta 1 dash. Both are compared, that error is given to amplifier, so it decides controls. So that controlled voltage VA is given to a motor. The motor will will be energized. As a result, the shaft which is attached to the table will be energized, or it will be moved. Okay. So this is the control device, this actuator, this is a process. Process in the sense we can say robot link. Okay. So now what is computer based control of a robot? Okay. So first we take a robot link. Okay. So this robot link, in the current position of a robot link or robot joint, that is measured by a position sensor. That information, for example, let us take joint 1. Okay, so joint 1 means it will produce theta 1. So here we have a comparator. This is minus, this is plus. So this is my requirement. This is my requirement for the second position. This is in first position. So when both are compared, it generates the error that is given to a computer. Okay, that computer takes the error and it will generate the actuation VA. So actuation voltage that is given to a motor, then that is given to the robot. This is how it works. So here's the role of a sensor is very important. And then here this instead of the amplifier, we can use a computer. So here we have many algorithms. The algorithms will work on this error, and then it will calculate the actuator voltage. That voltage is given to a motor, so that the motor will actuate the robot, so that your theta 1 is equivalent to theta 1 dash, or theta 2 is equivalent to theta 2. So this is the work carried away by this computer control. Okay, so this is how a robot works for a particular task. So sensor is very important because sensor would say the current position, current status. So now what is sensor? Sensor is a device, it converts one form. So one form is mechanical form. Converts mechanical form of energy to electrical form. Okay. And actuator vice versa, it converts electrical form into mechanical form. But both are used as a converter which converts one form of energy to another form. In sensor, it takes the mechanical, it senses the mechanical rotations or mechanical movements, and it gives the voltages, or it gives output as electrical form, which is voltage. Similarly, an actuator takes the electrical input, which is actuator voltage, that is given to a motor. Then accordingly, the shaft which is attached to the winding will also rotate. So electrical form is converted into mechanical form. So this is the basic concept of sensor. And then these are the basic classifications. We have internal sensors and external sensors. And then internal sensors, if you want to measure the position or velocity or acceleration or force, then you have to go for internal sensors. But if you want to measure, or if you want to measure this limit switch, and sorry, if you want to measure the external variables, like is there any obstacle? Okay, so in that case you have to use external sensor. First let us see what is internal sensor. If you want to measure position, velocity, acceleration and force, you have to go for, it comes under the calculation of internal classification of internal sensors. In position we have a linear potentiometer and rotary potentiometer, then incremental encoder, absolute encoder, and then we have both linear and rotary potentiometers. LVDT we have resolver. So all these are used to measure position. These are the various sensors for measuring position. And for velocity, we can take all position sensors, and we can take, for example, from this time to this time. Let's say example like 33 seconds to 40 seconds. So in this seconds, you can note down the position. So position with respect to time is your velocity. So you can use all position sensors to act like a velocity sensor. Then apart from that, we have tachometer and Hall effect sensor also. Then acceleration is all force sensors, okay? Because the derivative force equal to mass into acceleration. So when you get the force, you can easily get the acceleration. So force can be measured by using strain gauges, Hall effect switches, and piezoelectric switches. So these are the internal sensors. The external sensors will say that, or will measure how many obstacles are there, what is the impact. So for that, proximity. So it has a range. Within that range, if it finds any obstacles, then that will be detected. And then Hall effect also. Suppose Hall effect is when you give pressure, it produces voltage. So if any obstacle is there, that is pressed and then that voltage is produced. So likewise microwave, ultrasonic wave, and these are the various sensors. So our concentration or our syllabus is position sensor. In position sensor, we are going to see just potentiometer and incremental absolute input. Only these three we are going to see. And then velocity, we are going to see again all position sensor means we'll see this potentiometer and tachometer also we are going to see. And in force sensor, we are going to use strain gauges, and we are going to see how strain gauges are used to measure the force. Okay, so this is our syllabus. And in external sensors, we are using vision sensors. Vision sensors means it's a camera. Okay, so the camera will take the picture, then that captured image is undergone various processing, pre-processing, then finally it says what object is that. So that is your vision sensors. So our syllabus is only this one. Okay. So next, generally, what are the characteristics of a sensor? So first, before you select the sensor, you have to check the range, whether that range is suitable for your application. And then you have to find out the response time. So how long it takes. Actually, even there is a small change in the variable, your sensor has to detect that. So that is the response, highly responsive. And then accuracy, that I mean the actual value and the real value deviation should be very very minimal. That is called as actual accuracy. And sensitivity is how fast it is changing with respect to the input. So if you give the input whether it's suddenly changing means then more sensitivity. It takes time to change means it is less sensitive. Then linearity also. Linearity is we can predict the output. So constant sensitivity. If the sensitivity is constant, which means if the change in output with respect to change in output, change in input is same, then that is called as linearity. And repeatability, we know that the deviation from reading to reading, whatever, I mean, how many times we repeat, it has to be in the same point where we are intended to. Then resolution is it is the minimal change detected by any device. Okay, so whenever you buy or whenever you make a sensor, so you have to follow these characteristics. It has to follow the characteristics. So let's start with the first sensor, position sensor. So position sensor is used to measure the position. So here we are going to see rotary potentiometer, rotary pot rotary potentiometer, which means it will measure the angular position theta. Okay, so let's see how it works. So here this is the wire. So the wire is kept like this in this fashion. Okay, then one end is given as positive. So one end is given positive. Okay, positive, and then the other end is given as negative. So this is positive and negative. Okay, so here we have a wiper because someone has to measure what is the change. So here is the wiper, and then that wiper is also the wiper is also connected to a point because we are going to measure the voltage. So this should be ground. So this is the V out. Okay, so how, so let's take the entire resistances R. Okay, and then see this is the base position. So you have to measure this also. This is the current. Now the wiper is here. You have to measure this. Okay, so this measuring is theta. So now what is the formula? How to calculate the resistance? So here the overall resistances are in that it is moved by an angle theta. Then we have this voltage, input voltage. So V. Okay, so this is your theta current value. So how do you represent the current value? So you may have the maximum resistance in that how much angle will be swept by this wiper, and then that should be energized by the input voltage. Okay, similarly if your wiper is here, so this becomes theta. So if every time your wiper moves, this theta varies. Okay, so this is the resistance. So from this we can get the current angular position. So the moment we pass current to the electric wire, so due to heating, you have this I square R loss. Okay, so that's why there will be some heat generated, which will affect the performance. So if the heat is generated means that is which increases the temperature. Increase in temperature changes the resistance. So if there is an increase in temperature, the resistance will also change. That's why angular measurement may not be accurate. That is, if you use wire, then it may not be accurate because whenever we pass a current, it produces I square or loss. So this is for angular potentiometer. And the next one is linear potentiometer. So linear potentiometer is like this. So linear. So this is the overall resistances R. Then again this should be given given to positive terminal and negative terminal. This is positive and negative. This is V in supply voltage. And then here comes the wiper. Okay, so this wiper is, this is ground. So we have to measure this point. So this is V naught. So what is the formula for V naught? Output voltage. So here, if this is the one, so you have to measure this. So let's say this is R11. So R11 divided by the overall R, overall resistance into Vm. So this is how we can find out the resistance. So whenever there is a change in resistance value, that will be captured by the position. Okay, so this is the position sensor linear movement. Okay, but you have non-linearity because due to the temperature. Why temperature is changing? Because whenever you pass a current to that, you have I square R loss. So this creates more heating. That heating affects the temperature. When the temperature is affected, then this is a linear curve, okay, linearity. But if there is a temperature impact, then the curve will be like this. So this is non-linearity. So non-linearity is due to temperature, and if there is any friction between the physical contact. So here, this is the wiper. It moves up and down. It has some friction also. That friction also is due to, or which contributes non-linearity, and because of the motion you have wear and tear. Okay, so these are the limitations, but otherwise it is simple. Even you can get it for 150 rupees and wear off after some time, not immediately. It is not accurate because of this wear off. Hence it is not used in the industrial robotics, but for the laboratory purpose and then for educational purpose you can use this, but not for industrial purpose, because it is okay for only few days. Then after that, a non-linearity occurs. So this is your one more position sensor is encoders. Okay, encoders is also used to measure the position. So encoder is a simple device that can output a digital signal. So potentiometer output is analog signal, but encoder signal is digital signal. Digital signal means on and off output. So this on for some time, this off, on, off. So likewise it varies. So the pulses is the output. So the position is captured and output a digital signal for small, even a small portion is detected. So to do this, so how do we do that? So we have to take one encoder disk or a strip that is divided into small sections. So you can see this. So this is one section. This is transparent. Then this is opaque. So this is transparent. This is opaque. So likewise, you have to maker sections. Okay, and then you have to keep one light sensor on the this side of the disk, and then you have to keep a photo transistor on the other side of the disk, because light source is a light emitter. It emits light, and then so this is the disk. So this is connected to a mode actuator. So based on the actuator, it keeps on moving. Okay, so that movement can be captured as a pulse. You know how? So here this is transparent. When it is transparent, full light rays will pass through this. And in the phototransistor, the operation is it takes the input light and output is a voltage. So it takes it. So if your output is on, means then that particular point is transparent. If the output is off means then that particular point is opaque. So likewise, we keep on getting plus pulses on and off using this setup. So by counting the number of pulses, we can calibrate and we can say the current angular position. So the angular position is converted into a digital signal using this. So here the main thing is LED on one side and photo transistor on the other side. So this is how it works. Okay. So in that there are two types of encoder. One is absolute encoder. Another one is incremental encoder. So let's take this encoder. Okay, so here this is a disk, and then the signals is going to be, 4-bit. It produces 4-bit signals. So we have 4-bit means it is 2 power 4. 2 power 4 is 16. So you have 16 divisions. You should have 16 divisions. So 0, 1. So if you start from 0, it is 15 totally. So 0 to 15 is 16 divisions. So how do we do that? So first 0, 0, 0, 4 bits equal to 0 value. Then 0, 0, 0, 1 is 1 value. Then 0, 0, 1, 0 is 2. And then 0, 0, 1, 1 is 3. 0, 1, 0, 0 is 4, 0, 1, 0, 1 is 5, 0, 1, 1 is 6, and then 0, 1, 1 is 7, and this is 8, and then 1, 0, 0, 1 is 9, 1, 0, 1, 0 is 10. So likewise it goes on. So first let's take 0. So 0 means all the 4 are transparent. So you can see here transparent, 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 transparent. So there's 4 sections. The next section, the first one is opaque. So you can say that. So this is, so you can see the difference. So these are all zero. So these are all zero, and then this is, or we can say these are all opaque. This is transparent. So here, can you see this? This is one. Similarly, this one is shaded. So likewise, you have to make this pattern based on the output. So here I have selected as 4 bit. So just imagine if it is 4 bit means you have to have 6 sections. But imagine if it is 2 power 5, so you should have 32. Then imagine you have 2 power 6 or 6 bit, so it should be 64. So when you keep on increasing the number of bits, then it is so expensive because you have to make this design. But let's take this 4 bit, okay? So the pattern is made like that, and then here also you're going to have a light source and the photo detectors. Okay, this side photo detectors. So whenever you have a gap, then the light source will be incident on this photo transistor, and then that will capture the voltage and it gives you the voltage. Whether suppose if this is passed means, so here this we will have this as opaque. So all the channels will produce 0 0. Suppose if you when the disk rotates, if the disk rotates, let's see this portion is subjected to light source and the photo detector means, so for this only 1. So here you have 1, other things are 0. So likewise different patterns are generated. From that we can calibrate that this is the actual position, okay? But the problem here is it is precise, it is perfect, but it is expensive because based on the number of bits this section will be increasing. So number of concentric circles will be equivalent to number of photo detectors. So how many detectors we have? 1, 2, 3, 4. So similarly we have 4 concentric circles. This is 1, this is 2, 3, 4 concentric circles. It depends on the number of photo detectors. Hence increment, so because of these reasons, because of this expensive, and when you increase the number of bits, then automatically the whole unit will be bulky. So in order to avoid that, we are moving to incremental optical encoder. Okay, so this is your incremental optical encoder. So here is the disk. Then we have 2 points. One is A and then one is B. And here also we have a light source and the light detector. It detects the light and gives the output as A, B, Z. Okay. So why we are having two things means, suppose if I want to rotate this in one direction and then the other direction, both counterclockwise and clockwise means, so we have to take two signals. Suppose by tracking the, because this A and B are not located at the same point, some differences there. Okay, so if your A is like this, A is like this, and B is like this, so we can, this is your A, this is your B, so we can say that it is clockwise direction, clockwise direction. Similarly, if your A is like this and your B is like this, so this is counterclockwise. So in order to identify the direction, uh, two markings are the one is A and B, and you can see the displacement. So this is slightly distant, slightly displaced away from this, so that by seeing the picture we can say that this is clockwise or anti-clockwise. And otherwise it is simpler, it is not expensive, it is also precise, and the resolution is too good in this. So this is your incremental optical encoder. So next comes the force sensor. Okay, so this is one, now we used to say that this is called as Maltese cross configuration. So this is like a bangle. Okay, so someone, I mean, the robot can wear this bangle, and then if you wear this bangle, and suppose if the robot is picking something with more stress, means then the entire setup will be stressed. That stress is captured. Okay, but generally force cannot be measured directly; it has to be measured indirectly. For that we use strain gauge. Okay, so strain gauge is a simple transducer, a simple resistor. Okay, So in order to get the change in resistance, we have to connect strain gauge in the Wheatstone bridge. Okay. So this is strain gauge 1, this is strain gauge 2, this is strain gauge 3, this is strain gauge 4. Okay, so here we have to measure the output at this point, and then at this point we have to give a voltage, supply voltage. So here whenever this is strained, or whenever either one of the strain gauge is strained, then that you can measure that voltage that will be reflected in this voltage, because the formula is V naught, sorry, V in is the reference voltage, V in. So V naught equal to V in into, you can take common. So, so this is grounded. So let's take R as strain gauge means it produces R1 resistance. So this is R2 resistance, and then this is R3, then this is R4. So how to do that means, so here this one is R1, R2, R3. So the formula is R3 divided by this swing R1 plus R3, okay, minus the next one is this resistance R4 by R2 plus R4. So likewise, I'll write clearly here, V naught output voltage is equal to supply voltage is this, and then check these R3 and R4 are connected to the ground. So let's take that as a numerator, R3 by R, this resistance is this swing R1 plus R3 minus R4 divided by R2 plus R4. Okay. So whenever there is a change in, I mean, whenever the stress changes, stress to the strain gauge changes. So stress means what? It's a kind of force. Okay. Force equal to pressure equal to force by area. Okay, force equal to this. So whenever you give the pressure, then this pressure and the area will give you the force. Okay, so that is why we are using strain gauge to measure the force. So let's see in this picture. So here we have a deflection bar 1. This is deflection bar 1. This is deflection bar 2. This is deflection bar 3. Deflection bar 4. In each bar, you have two pairs of strain gauge, which means four strain gauges. That four strain gauges are connected in this fashion. So each strain gauge will give you two outputs. One is W1 and W2 here, because it's Wheatstone bridge first one, Wheatstone bridge two out. Likewise, for every deflection bar, you have a Wheatstone bridge output, because it is contained in this fashion. So whenever you wear, I mean, whenever the manipulator wear this bangle kind at the end effector, and when it grabs or when it grips something, so automatically the deflection bar will be stressed. That stressed will be captured by the Wheatstone bridge. So the Wheatstone bridge output can be realized in W1, W2, etc. Then from that we can calibrate the force. So what is the current force? So this is how it works. Okay. So let's see that how it works. So here, since force means you can have linear force, Fx, Fy, Fz. Okay, then you have a rotating force also. So that is moment, Mx, My, Mz. So this sensor is used to measure linear force as well as torque. Okay. So here we have a Wheatstone bridge output W1, W2, W3, W4, because there are four pairs. So totally eight. So W4, W5, W6, W7, W8. So these are the Wheatstone bridge output whenever the particular strain gauge is okay. So we should have some calibration value. So C1 for the first row, and then C11. Okay, so next C12, next C13, up to C18. Okay, here C21, C22 like this. So it goes on. So like here C61, C62. So this is the matrix. So Fx equal to, you have to multiply this. So that will give you the force component on x direction. Fy equal to this row and then this. So likewise. So in this, when when the end effector grips something, it's not that all the strain gauges will be affected, only very few. So in that case, that W1 has the value, but W2 has some value A, or this may have 0. So accordingly, the equation changes. So let's see how to write the equation. Okay. So first we'll write the equation for Fx. Okay. So here Fx is when you lift this, which means when this is strained, when this is strained, so you have the I mean the suppose or when you lift this, suppose when you wear a bangle, if you have a force in this direction, automatically this deflection bar and this deflection bar will be affected, which means W3 and W7 will be affected. So we'll write the equation. So W3 and W7 is affected. And then the calibration matrices, so this is the first row, so C1, and then the component is C. So here, this is seventh one, so it is first row but seventh column. So this is how we have to write the equation. For other parameters like W1, W4, W5, all are 0. Similarly, Fy. So how to write Fy? So here if the force is in this direction, so W1 and W5 is taking part in this. So how do you write that? So W1 and then W5. Other Wheatstone bridge outputs are 0. So this is a second column. So second calibration matrix C2 1. And then this is also second column. So C2 5. Okay. Then WF set. So the other Wheatstone bridge outputs are for this. So what is missing? So W1. So next one is W2. And then this is the third row. So C3, then 2. Okay. W1, W3, then W4 is missing. W4, and then this is third row, and then 3, 4. W5 is here, so W6 is missing. W6, C36. Then W7 is there, W8 is missing. So W8, C3, 8. Okay. So these are the linear force components. So if you want to measure the force in x direction, you have to take down these values and you can measure the force. Similarly, we can write for mx. So mx means here. Okay, so it revolves like this. If it has to rotate like this. Okay, so if it rotates like this, so this component W4 and W8 will be affected. So let's write that. So W4 and W8. So this is in first row, second row, third row, fourth row. So C4 4 plus C4 8. Okay. Similarly, WMY. So MY means you're rotating in this fashion. You're rotating in this fashion. So W5 and then W2 will be taking part of this, taking part in this. So W2. So W2 and because it is you're rotating like in this fashion, sorry, in this fashion. So you have to take like this, so this part. So you have to rotate. So just imagine it is rotated in this fashion. So here W2 and W6 are taking part. So W2 and W6 because it rotates. So yeah, W2 and these two. Okay. So W2 is in 3, 4, 5. So C5 2 and then C5 6. So MZ are the remaining thing. So W1 is missing. So it is sixth row. Then W2 is there. W3 is missing. W3C63 and W4 is there. W5 is missing. W5C65 and the 6 is here. 7 is missing. W7C67. Okay. So likewise, we can write the coordinates and then you have to calculate. So this is how your force sensor works. So I'll repeat again. So this is like a bangle. This force sensor is like a bangle. So the end effect for the end effector you can put the bangle, and then when the end effector picks something or when it grabs something, so either one of the deflection bars will be affected, or you can experience force in any one of the direction, or you can experience moment in any one of the direction. Accordingly, the particular because all are connected to the Wheatstone bridge. So here this Wheatstone bridge produces W1 and W2. This Wheatstone bridge produces this output. So that has to be captured and you have to substitute and you can find out the force in this particular direction. So directly we cannot measure force, but we can calibrate force or we can derive force from strain gauge measurement. Okay, that's all for today. Thanks for watching. Thank you.